I got really confused with the whole equation
Okay,
and then the velocity.
sure.
I had to like look it up, and apparently there's like a conversion factor between feet second over squared seconds to BTUs over LBM.
Okay.
Yeah, two. One I had two. Kind of the same thing, the conversion factor.
Mm-hmm.
1,000. Just trying to find where I got it.
Because I also got as an output, I got like slightly warm water.
Okay.
In this question in English, it gave us empirical units. Can we like convert them to SI units and then have our answer in SI units, or since
Yeah. Yes, for sure. You can always put your answers in SI units.
Okay, so because I put my answer in Celsius, so I was wondering if they change their own thing.
No, you don't have to.
What values did you get?
220 degrees Celsius. Roughly.
That sounds more reasonable.
Okay, so we have a thing generating power. Isothermal expansion means the temperature stays the same.
How are the projectors warming up?
They were on before, weren't they?
Still talking about the daily sun, right?
Yeah. Okay. So this thing, it goes through an isothermal expansion.
Oh, that's a different.
What?
It's a different problem.
Isn't
First law of control volume part 1 question 2, it's only doesn't have to be part of 6.
oh.
Introduction to engineering.
Oh.
Where's
That's a different semester.
Yeah, thermodynamics.
Okay, first law for control volumes. Number 2. Okay, so it's a nozzle. You have, so yeah, that's a pressure and a temperature and a velocity. I guess.
I can just cross out everything except for
Okay, let's get to that in a second. So we got a pressure and a temperature and a speed at the inlet, and then a pressure and a speed at the exit. It's well insulated, so there's no heat transfer. Steady state, neglect potential energy effects. We are going to take into account speed effects. So I think, we're going to have to look this stuff up in the website. Let's convert it. So 300 pounds per square inch. and convert that to pascals. So that's 206, no, 2,068,427. Okay, so at the inlet, we have a pressure of 206,8,427 in pascals. And we have a temperature while I have this typed in, let me just do the pressure at the exit. So this one at the exit is 40. So that goes to 275,790 pascals. And the temperature, 600 degrees Fahrenheit to Celsius is 315.6 degrees Celsius. And then the speed, 100 feet per second. So that's just 100 divided by 3.281. So that's 30.48 meters per second. And then at the exit, this is 548.61 meters per second. Okay, this is a nozzle. So does this stuff make sense? Yeah, we expect a nozzle to have a high pressure and a low velocity at the inlet, and a low pressure and a high velocity at the exit. And so now it's steady state, so I'll just start with this and then cancel from there. M dot times the quantity H inlet. We're ignoring the potential energy stuff, so I'll just do VI squared over 2, and then minus M dot times the quantity H exit plus V exit squared over 2. It's well insulated, so there's no heat transfer. It's a nozzle, so there's not going to be any work. And so we can divide everything by the mass flow rate, but divide both sides by the mass flow rate, and you get that HI plus VI squared over 2 is equal to HE plus VE squared over 2. Well, we have, so on the website, we can look up HI because we have the pressure and temperature, and then we can calculate HE. And we're trying to come up with the exit temperature. So let's see. So we're doing water. The temperature was 315.6. We want international. The pressure was 2,068,427. We want it in kilopascals, so that's 2,068. Thank you. And so we get an enthalpy of 3058. This is in kilojoules. So HI is equal to 3058 times 10 to the third joules. And so we have 3058, put these in here, 3058 times 10 to the third plus 30.48 squared over 2 is equal to HE plus 548.61 squared over 2. And so I got the enthalpy at the exit to be 2.91 times 10 to the 6. And now we're trying to find the exit temperature. So let's see. Our pressure at the exit was 275,790, or 275, let's call it 275.8 in kilopascals. And then hopefully there's enthalpy. Yep. So, and our enthalpy, this is in kilojoules. So, we want 2.91 times 10 to the third kilojoules per kilogram. Or 29,100. And we get a temperature of, that is a crazy 2.9. I have one too many zeros, don't I? So the temperature is 221 Celsius. With this stuff, in this problem, there's not a formula. You just have to use a table or the website.
Professor,
Mm-hmm.
so in these problems, we should just convert it to metric right off the bat.
You don't have to. I wasn't sure that it was going to have pressure, and that was sort of a weird. So let's see what it uses for pressure here. Let me write this down. 221.1.
Instead of converting the kilojoules or just divided the velocity squared by a factor of like thousands, and then I got the same answer, but it's suppose. Instead, I could just taken the kilo part out of the specific enthalpy.
Yeah. So it looks like they use pounds per square inch for absolute pressure. What did this use? Pounds per square inch. So it looks like we could have just done that whole problem maybe with their units, but I don't know. It's fine with me if you convert or don't, but you do have to be careful with the units, especially in these problems that have velocities or heights where you're using potential or kinetic energy, because you're always going to want to express those in, well, if you're using SI units, you're always going to, if you're using international type units, you're always going to want to convert to SI units before you include that stuff, or your units are going to be out of whack. Any other questions about that one? Any other homework questions you want me to go over? All I'm planning to do today is just a couple of example problems. So, I'd be just as happy to do these as the ones I have.
Number 4.
Okay, sure. Okay, so this is a diffuser. So where do we expect the pressure to be bigger in a diffuser, the inlet or the exit? Yes. And where do we expect the speed to be bigger?
Inlet.
Right, inlet. So, and it's the exact reverse of a nozzle. Again, we have these funny, but okay, so now we know we can use, we can just use the website with these units.
I have a question. So if it's steady state, we can just neglect the speed.
So if it's okay, so steady state means that dE dt is 0, and it also means that mi dot and me dot are the same, so you can just call those m dot. But it doesn't mean that you can ignore the velocities. That's a separate thing, because you could have it steady state and still have different velocities at the inlet and the exit. Okay, so we have that 0 is equal to q dot minus w dot plus m dot times the quantity hi plus vi squared over 2 plus gzi minus m dot times the quantity he plus ve squared over 2 plus gze. At the inlet, the pressure is 100 pounds per square inch, and the velocity is 1,200 feet per second. And at the exit, this is 300 pounds per square inch, and the velocity we're going to treat as 0.
How How do we know the velocity? Oh, is it because it said the velocity is like
Yeah, negligible. Yep. So that means ignore it. Um, the so the diffuser is at steady state. We're gonna ignore potential energy effects. Um, insulated, so this is 0. Nozzles and diffusers don't have any ability to change volume, so that's 0. Now you can divide both sides by m dot, and you get the same thing that we got before. So hi plus vi squared over 2 is equal to he plus ve squared over 2.
The velocity is negligible, right? It's not like the exit.
That's right. Yeah. Right. So this one is going to go away. So we can ignore this. Okay, so now we'll have to think a little bit. The units it gives us, whether those are units that fit together with everything we have. Hopefully it is. Pressure. Okay, it gives velocities. Okay, so we can. Oh, it's a saturated vapor. Okay, so saturated vapor means we only need one property to look things up. So
put in quality equals 1, right?
for a saturated vapor, quality is equal to 1, right? So, and then a pressure of 100. So at the inlet, and this is refrigerant 134A. The quality is 1. The pressure was 100, right? Is that what I said? And so the enthalpy is 113.8 BTUs per pound mass. So 100 BTUs. $113.8. So HI is equal to 113.8 BTU per pound mass. Now, if you're sure that these units jive with feet per second velocity, then you can use that. I am definitely not sure that that's true. So you could Google stuff and figure out what those units are equivalent to. So let's see.
Yeah, it's supposed to be like you divide the like velocity thing by 778.17
For what?
to get the BTU over LBM from the feet squared.
Okay. Like you looked that up or figured that out like
Yeah.
when you were okay. Yeah. So I mean,
I was like, why? How would it make the enthalpy like huge like that? And it turns out you got to divide it.
two. So what would this be? So that would be feet squared per second squared.
And in metric, it is easy because they design metric to be practical. You don't have to do anything.
Yeah, these can get a little messy. BTU.
I noticed that on the website it uses the English or numerical units automatically. Is that because in
Say it again.
just whenever I open up the window, it just always pulls up English or imperial units
Yeah.
automatically? Is that because in the United States it's more common to use calculations?
I don't know what their thought process is on that. I suppose that's probably true. So yeah, you're right. So the conversion would be 778. So okay, so 113.8 is equal to 88,555.6 feet squared per second squared.
You get that conversion.
I just went to ChatGPT and asked
Okay.
what's the conversion from BTU per pound mass to feet squared per second squared. So yeah, I don't care how you do your conversions, but just get in the habit of making sure that the units you use all make sense with each other, you know?
Well, wouldn't, for the next step, I just put that in,
Mhm.
the enthalpy, and then pressure equals the 300 pounds per square inch. So we need that in BTU or LBM to put it into the calculator.
Well, you need it to match with the units of the speed in the equation in order for this equation to give good results. So this is the part where you need to convert something for them to match. And so
So we can't just put it like 1200 squared over 2 times 778.1.
yes, you could do that. Divided by though, right?
Yeah, divided by.
Yeah. Okay, so HE is equal to 808 556, and this is in feet squared per second squared. And so now I'm going to divide this by 778.169, and that gives 1039.05 if you want this in BTU per pound mass. We want the exit temperature, and so we needed to convert to those units so we can use this website, 1039.05.
Temperature and the specific enthalpy to get the temperature.
Right. So let's see, so the pressure was 300, 1039.05. 300. Okay. So the pressure is 300. The enthalpy is 1039.05. And we get a temperature of 2359 Fahrenheit. Okay, so be careful with the units. When I on exams, I will never make you mess around with units. I'll just always put everything in SI units, but I think it's probably not bad practice to get used to dealing with that. But remember, like you do all this work, you know, and if you're not careful with the units, your answers are going to be nonsense. So take the time to check, you know, like I think it's kind of natural for people to be like, I bet these work together or whatever. But that's just a bad habit to get into. Don't do that. Take the time to make sure the units match. And if you can't figure out how to make sure they match, just convert everything to SI units. And those conversions are so easy with, you know, Google or Chat GPT or whatever, you know. So, okay. Any other homework questions? Yeah. Yeah. Mhm. It probably is. I wouldn't be surprised if those are solutions to like a different. So I'm sorry about that. That's a mess. But what?
For that previous one that we did,
Let's do it.
how many feet squared over second squared did you get from the 1187? Or should I just show it to you after class? I'm a bit confused.
Um. Okay. For what? For the one we just did?
Yeah.
What did I get for what?
So we took okay, it's 113.
That was what I got from the table or from the website.
Okay, so I got a different value for some reason.
Hmm. Okay. What number? Number 3? Okay. So we got refrigerant. It enters a condenser. Steady state. Um, this is in conservation of mass, so we know we're going to use this equation in some way at least. It's in steady state, so that means m I dot is equal to m e dot. You know, there's just a single mass flow rate. Uh, at the inlet, we have a pressure of 9 bar and a temperature of 50 degrees Celsius. And we know that the area of the inlet is, so this is a 2.5 centimeter pipe. I'm going to assume that's round. So the area is pi times 1.25, the radius. Let's do this in SI units. So 0.0125 squared. So that's 4.91 times 10 to the minus 4th meters squared. At the exit, the pressure is 9 bar. The temperature is 40 degrees Celsius. And the velocity is 2.5 meters per second. So we're going to use the fact that m dot is equal to the area times the speed divided by the specific volume. So using this with the mass balance equation says 4.91 times 10 to the minus fourth times the speed at the inlet, which I don't think we're given. Divided by the specific volume at the inlet is equal to the area at the exit times 2.5 meters per second divided by the specific volume at the exit. And these two things have to be equal to 6 kilograms per minute, which is 6 over 60 kilograms per second, so 0.1 kilograms per second. And we have everything we need to look up VI and VE. So at the inlet, 9 bar is equal to 900 times 10 to the third, or 900 kilopascals, and 50. So 900, the temperature is 50 Celsius. And so we're looking for the specific volume. That's 0.025. And then for the exit, we have, are those pressures the same? Yes. So 940 Celsius. So 0.023. And now you have two equations for two variables. So the first one says 4.91 times 10 to the minus 4 times VI over 0.025 is equal to 0.1. So the speed at the inlet is 5.09 meters per second. And then the second equation says 2.5 times the area divided by 0.023 is equal to 0.1. So the area at the exit is 9.2 times 10 to the minus 4 meters squared. I didn't even look what it asked for, but that seems like a good guess at what it's going to ask us for. What if it's like, what is the airspeed velocity of a laden swallow? You guys know that movie?
Oh, yeah. Oh, the Holy Grail.
Yeah. Okay, what's the velocity in the exit? Yeah. It asks for diameter, not area. So then you have to, use the formula for the area to come up with the diameter. Any questions about that one? Okay. Well, happy long weekend. Except for most of you, I'm going to see in 10 minutes. But